Hi, my name is Andrey Kudryavtsev. I'm from Intel. I will spend 15 minutes of your time to talk about storage and what Intel is doing for the storage. Products related to SSD technology on Optane SSDs and NAND technology, and overall Intel strategy, how we see these components to be integrated into HPC solutions, which is, I think it's quite interesting. So, this concept's not new, but there are many developments that happened recently about how we tier the data into the multiple slices and how we optimize the data location. And obviously, from a computer architecture, there are tiers of the data. Usually, we have less tiers in a like a standard environment where you have a hard drive, so you might have a memory, and you have nothing in between. In a today's environment, you obviously have some SSD options because it gets more affordable, and in a desktop computer and in a server computer, it just makes more sense to run applications directly from SSDs. But still, the point that we are doing here, that there is a significant gap in the performance between the SSD performance and between the memory performance for the overall bandwidth, I/O specifics, and especially for the latency. And that's the case when you try to address the data and put the data in multiple places, especially when you run out of memory. So a couple of years ago, we came with their idea for delivering a special set of products which are optimized on a new memory architecture, and that name got Optane. So Optane is a marketing name to the media technology, which is a byte-addressable technology, and unlike NAND, it doesn't have limitations for operations, how you do that in NAND for sectors, pages, blocks. I will explain it a bit later. But basically the whole idea that it helps us to deliver totally different latency characteristics of that media, which places that media somewhere in between of a standard NAND-based SSDs and memory tiers. And so it depends how you place that memory as a storage device or as a memory device. It can be one or another, or in certain cases that can be both at a time. So there are two products families. Both of them have a name of Optane. One is Optane SSDs, and these are PCI Express SSDs that goes into the PCI Express slot, runs on NVMe protocol, and that's basically a block device, very high performance. I'll talk about that a bit later. And there is another set of products which goes into the memory slot, into the DIMM form factor slot, and this has the name of the Optane DC persistent memory. And unlike a standard memory, it has a persistent characteristics to the memory, so the data stays over the reboots of the system. Both of these technologies have a foundation of the Optane media architecture, and the main advantage of that media, as I said, it's a bit addressable, and there is no overhead when you do operations. So it's a write-in-place media. Every time you do some writes, you don't need to do a preparation of that media. You just go and straight overwrite a condition of that memory cell, no matter what was that. Was it 0 or 1, you just write the data that you need. With a NAND technology, you have to do erase cycle first when you write in the data. So that's why basically there's a main difference between these, how you operate with that. And that's more important that when you write in the data with the NAND products, you unfortunately operate with the pages, so you have to combine the multiple sectors into a page and write that page together. And the complexity even going when you basically operate with erase cycles, you erase it by erase blocks that consist of a number of pages. So Optane Media doesn't have all of that, and that's why we are able to deliver very high performance storage products and totally new memory concepts that allows you to do a persistency. Going a little bit more how NAND operates so you understand that probably in more details. NAND has significant advantage. It's easy to scale. So NAND technology today works in a 3D space, so it's called 3D NAND. The reason for that because it goes to the multiple layers. So we are not just packaging the multiple chips inside a chip package. We are growing the number of layers within the, let's say, the one slice of that chip. And currently technology is running on the 64-layer technologies. Intel has a very way look to how we growing that number of layers, but limitation of that technology is still there. So it operates with blocks. And for instance, when the user writes some data, you run it on empty space, and these spaces, well, pre-erased or just empty when you got the drive out of box. And over the time, obviously, you get some invalid data. And when you delete the data actually from NAND, you are not deleting the actual data. You only mark that that data is invalid. And this is why you have these trash cans there. And what SSD controller is doing in the background, basically, it does what's called garbage collection. It combines all the data which is invalid, basically from all the locations, and aggregates only the valid data and runs into an empty place. And this is something that happens always in the background. No matter what you do, there is a set of these operations that SSD controller has to run to manage that data because of this overhead of managing pages and erase blocks. The problem starts when you do that very high IO-intensive applications, such as random writes, for instance, because you are no longer able to do these operations in the background. And at some point, and that's what you see, so your typical random write performance is lower than your random read performance because you must manage these operations while running your real user workload. So Optane drives, they are not doing that at all because there is no that condition where you have to move the data, have to manage the data. It's all right in place. You go just to the location that you need, and you write the amount of data. And in case of our SSD, it's a sector size. So we operate with like a 512-byte sector size. In case of a memory products, this is a cache line. Speaking of SSDs, and that is number one advantage for the latency and for that balanced operations. Number two advantage is extremely high endurance. Unlike NAND-based SSDs, which are, in the best case for our product generations today, is 3 drive writes per day. So we can overwrite the drive 3 times of its capacity every day during the warranty. And warranty for data center SSDs is 5 years. So we can do that only 3 times a day. Of course, you can do more, but basically you can run out of available cycles of a media, so you will run faster, basically, than your warranty. While Optane SSD is rated to the 60 drives per day, so you have significant advantage of the endurance of a media. So these drives typically go to the write-intensive applications when you really write a lot to the media. There is a classic test that we run. It's called read under pressure test, and what it does, we create a workload where we always write in the data to the device, and this is that workload that you see here as a steps in a yellow line, and that is basically megabytes per second that we generate, starting from 10, 20, 100, 200, 400 megabytes per second that we're constantly writing. And while writing the workload, we also measure the read response. So for instance, you do a memory checkpoint and you're constantly writing the data from memory, and at the same time you have to read something for any reason. And this is what we actually measure, the read latency response. And with NAND-based drives, this gray line, which gets bigger, 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 and this is your read latency response. This is how drive responds to the reads operations while doing the writes at the same time. And what you may see is just not just growing straight. The range of these latency response is also growing, and at some point, basically, you're losing your quality of service that you may have for any reason. It can be your virtualized environment, and one VM is running constantly some writes operations, and another VM needs to get the data, and this is where you'll be impacted. For Optane SSDs, this is not the case, and this latency response is that straight blue line near the 0. And basically, this drive is constantly responding with the same latency, no matter how much write pressure you put on the drive. So that basically makes these drives is ideal caching scenario where you read and write at the same time, and you need to have a balanced operations of the drive, and you need to have a high endurance. And majority of the use cases that we do for storage are around using these drives to accelerate standard SSDs, standard NAND-based SSDs. And such as that can be a caching, that can be a metadata. We have great stories for using these drives as a metadata tier in Lustra and data and metadata. That can be your journal devices for your Ceph installations. If you do that, it makes total sense to allocate all your journals just on a single Optane drive and improve the performance of your Ceph installation. And that can be anything else that can differentiate data from metadata or data from indexes. And by doing that, you can certainly accelerate the performance of your storage and not necessarily need to migrate to all Optane products. So this combination of using Optane SSDs with the standard NAND-based SSDs really gives you the advantage. Now let's speak a little bit more about what we can do with Optane DC persistent memory. So we take that Optane media and now integrated that in a form factor of a DIMM model that goes to the DIMM slot. And the size of these models is up to 512 gigabyte, and you can populate them up to 6 per CPU socket, so that gives you 3 terabyte per socket of maximum capacity of that memory. Typically, you have to populate it with balanced DDR4 configuration. So, for instance, in the latest generation of Xeon Scalable processors, we have 6 channels per processor. And all of these 6 channels are recommended that you populate with DDR4 sticks first to get them in a balanced mode. Well, basically the normal practice that you populate with DDR4 memory with a balanced operations. And then you can populate it with 1, 2, well, all the 6 configurations of Optane DC persistent memory. And that can give you capability of memory or persistent data store. So I'll talk about that a little bit later, the 2 modes of operations. But basically, that determines your maximum memory size, and it can coexist together with DDR4. How different that performance-wise to the DDR4? And performance-wise, and this is what we are really showing a lot here, that is a matrix of your bandwidth to the latency response. And if you look at that, so for instance, let's consider a standard NAND-based SSDs. That's a green line. So you start your latency at about 100 microseconds, and this is where your single I/O operation latency. And you deliver all the way through, even to the half of a millisecond, depends, well, how many I/Os you push to the drive. And finally you get to the, well, it's a hockey stick cliff, where you basically no longer able to get the bandwidth, you're only growing the latency. In the same way, Optane SSDs, they start at a 10 microsecond latency. That's your single I/O. It's a 10 times lower latency. That's why this device is really faster. And we keep within this latency no matter how many I/Os you put to the drive, as I already presented that with the right pressure test. And again, that sort of a cliff happens when you stop scaling your bandwidth. You're no longer able to deliver the bandwidth, and done. So that's your maximum capabilities of the media. With Optane DC persistent memory, and it's a performance per DIMM. We're starting at the range close to the DRAM latencies, and we're growing that range up to, well, about 5.5 gigabyte per second per DIMM. But the main idea that we can basically scale that in the same way how DRAM bandwidth scales with interleave. As more memory sticks you put in the platform, as higher aggregated bandwidth you have. So very different on the performance-wise, but this difference is scalable. So now about operations mode. There are 2 operations modes that can be interesting to you. One is very simple. It works on any operating system and totally managed by the hardware, and it's called memory mode. In memory mode, you see the capacity of a system memory equal to the capacity of Optane DC persistent memory, and DRAM that has to be in the platform works as a cache to that memory. So basically, it's a hybrid memory architecture. You can run huge capacities of, like as I said, in the case of a 2-socket configuration, that can be up to 6 terabyte of overall memory for the 2-socket server. And you'll see that totally transparent to the operating system. Operating system is not aware that it runs on a hybrid memory. It thinks that it's a real memory, and so it's capable to utilize basically on everything that can run on x86 processors. In AppDirect mode, this is where you have persistency, because in memory, even the technology can be persistent. We run it as volatile because there is no persistent semantic when you run it in memory mode. What you need to do to get the non-volatile characteristics to run it in AppDirect mode, and that requires using a software libraries called PMDK. And basically, that's a library that you use once to initialize your memory, or for instance, if you do a malloc, you just refer to that library and you get the pointer to this memory. It's slightly more complicated, but it's very easy to get that integrated into the existing codes, but you have to modify the code in order to leverage AppDirect capabilities of the media. So, and in general, the way you populate the system, you can populate it with 6 sticks of DRAM and 6 sticks of Optane DC persistent memory. Or you can scale that. You say, I want to still have 6 sticks of DRAM, and then I put only 4 sticks of the Optane DC persistent memory. Or I can put only 2 sticks, or even I can put 2 DRAM, 1 Optane DC persistent memory, 2 DRAM, 1 Optane DC persistent memory. All of these configurations support it, but just expect that the performance will be impacted as you move to this direction, simply because, well, you share the memory channels, and in this case, you have less capabilities for interleave, while in the first configuration, you have the best and optimal configurations. So, finishing my presentation, there are multiple opportunities for running these for different workloads, and we see lots of attraction for AI applications, for machine learning applications, and especially in HPC for the standard configurations, where you need a big memory for scientific codes, and these would be some of the projects that you really can look at. We published for supercomputing a number of scientific papers, which are publicly available right now, and I highly encourage you to look at that and get up to speed with new hybrid memory capabilities and use non-volatile persistent characteristics for your applications. Thank you.
Perfect. Thank you so much.